Quantum Gravity, It's Easy by Eugene Stefanovich. Let me start this presentation with a quote from Lee Smolin. He said, Problem 1. Combine general relativity and quantum theory in a single theory that can claim to be the complete theory of nature. This is called the problem of quantum gravity. From this quote, we can gather a few important points. First, many physicists would agree that quantum gravity is the number one problem in modern theoretical physics. If such a theory is found, most likely it will be the complete theory of nature. Most existing approaches seek quantum gravity as a combination or a hybrid of general relativity and quantum mechanics. However, despite many decades of relentless efforts, we still don't have even a framework of the future theory that everyone would agree on. In my presentation today, I'll try to present an alternative way to quantum gravity. Outline. First, we will recall briefly the Newtonian theory of gravity. There is absolutely no problems to quantize this theory, though the resulting approach is non-relativistic. Then we will talk about the traditional view on relativity, which is associated with the names of Einstein and Minkowski. In this approach, the true geometry of the world is a four-dimensional pseudo-Euclidean geometry where time and position are equal coordinates. The general theory of relativity keeps the Minkowski spacetime, but allows it to have a non-zero curvature. The equivalence between space and time coordinates is retained in general relativity. And this is where we meet a fundamental contradiction with quantum mechanics. Because in quantum theory, position is an operator of observable, while time is just a numerical parameter. We will offer a solution for this paradox by drawing our attention to the Wigner-Dirac version of relativity. This approach can be easily extended to cover the gravitational force. And we will show that there is no problem whatsoever in explaining most experimental effects that are usually attributed to general relativity. We will prefer to formulate the Newtonian theory of gravity in the Hamiltonian language. Here, the Hamiltonian is the sum of kinetic energies of the two masses plus the gravitational potential energy. The two masses interact by an attractive potential that is proportional to the product of masses and inversely proportional to the distance. Despite its simplicity and total neglect of retardation, this Hamiltonian is doing a superb job at describing dynamics of the solar system. There is only a tiny discrepancy regarding the orbit of Mercury, and we will talk about that later. Remarkably, this approach is very easy to quantize. We can keep the same form of the Hamiltonian, just replace classical phase space variables of momentum and position by quantum operators in the Hilbert space. Strictly speaking, masses become quantum operators too. The quantum commutators can be obtained by analogy from classical Poisson brackets. The beauty of this theory is that one can easily switch between classical and quantum modes of description. The classical and quantum Hamiltonians look exactly the same. In the quantum mode, the Hamiltonian is a function of Hermitian operators. But if we pretend that we are dealing with functions on the phase space, then we'll get the classical description. So, formulating a Newtonian quantum theory of gravity is not difficult at all. Moreover, this theory has been confirmed by a number of experiments. For example, it was possible to measure the dynamics of slow neutrons above a horizontal mirror. These measurements confirmed indirectly the eigenfunctions and eigenvalues of neutron stationary states in the Earth's gravity. So, let me summarize the story of Newtonian quantum gravity. First, this theory is simple. Its quantum predictions agree with laboratory experiments. But it also has obvious drawbacks. First, the theory is non-relativistic. And second, it cannot explain such well-known gravitational effects as the Mercury perihelion shift and light bending, etc., etc. These effects are explained traditionally by general relativity, which is a bit more sophisticated version of the special relativity developed by Einstein, Minkowski, and others in the beginning of the 20th century. Let me say a few words about the special relativity. The heart of the matter are Lorentz formulas that describe how space-time coordinates of events transform between inertial reference frames that move with velocity v with respect to each other. It is important to note that these formulas are regarded as universal, meaning that they are applicable to all types of events regardless of their physical nature. Einstein proclaimed this new paradigm as follows. Every general law of nature must be so constituted that it is transformed into a law of exactly the same form when, instead of the space-time variables x, y, z, t of the original coordinate system K, we introduce new space-time variables x prime, y prime, z prime, t prime of a coordinate system K prime. In this connection, the relation between the ordinary and the accented magnitudes is given by the Lorentz transformation. Or, in brief, general laws of nature are covariant with respect to Lorentz transformations. Let us now change the notation a little bit to rewrite Lorentz transformation formulas. Instead of the velocity v, we will introduce a parameter theta called rapidity. The hyperbolic tangent of theta is equal to v over c, where c is the speed of light. In this notation, the usual relativistic square roots transform into hyperbolic cosines and sines of theta. If instead of time t we will use the product ct, which has the dimensionality of length like the three other coordinates, then Lorentz transformations will acquire a rather simple and symmetric form. Why this result is significant? Because in a four-dimensional space-time where Ct is the force coordinate. These transformations describe a so-called pseudo-rotation, preserving the interval between events. This is remarkably similar to usual three-dimensional rotations that preserve distance between points. The only difference is that rotations use ordinary trigonometric functions, while boost transformations involve hyperbolic sines and cosines. This suggests a mind-boggling revelation that perhaps the entire Einstein special relativity can be expressed as a unification of space and time into single four-dimensional geometry, where the role of distance is played by the interval. Since the interval involves both positive and negative signs, this new geometry is not Euclidean, but rather pseudo-Euclidean. And this bold step in understanding of Einstein's theory was made by Hermann Minkowski in 1908. Here is what he wrote at the time. From now onwards, space by itself and time by itself will recede completely to become mere shadows, and only a type of union of the two will still stand independently on its own. Three-dimensional geometry becomes a chapter in four-dimensional physics. In 1915, Einstein made a step further by developing the general theory of relativity. Its central idea is that gravity is caused by the curvature of the Minkowski spacetime. Just as in special relativity, the four spacetime coordinates are regarded as equal or interchangeable. But this approach is impossible to quantize because in quantum mechanics, space coordinates x, y, and z are Hermitian operators, while time t is a classical parameter. Let us now discuss this important point in a bit more detail. What are physical observables, and why do we say that position is an observable? We expect that physical observables can be measured in physical systems, and the results of measurements depend on the state of the measured system. In the lower left corner of this figure, I indicated my observer by a pair of binoculars. This observer studies physical systems such as a candle or a fly. These observations produce values of the legitimate observables such as velocity, mass, or position. We can say confidently that position is a property or attribute of a physical system. Expressions like position of the candle or position of the fly are definitely meaningful. In quantum mechanics, we describe the position observable by a Hermitian operator which has a specific spectrum, eigenstates, and permits of a probabilistic interpretation. Now, what about time? To quote-unquote measure time, we do not need to look at any physical system. Time is measured by the clock, which is a part of the reference frame, similar to the coordinate axis. Clock readings do not depend on which system we are observing and what is its state. So it would be reasonable to conclude that time is not a property or attribute of a physical system. Expressions like time of the candle or time of the fly do not make sense. Therefore, in quantum mechanics, time is not an Hermitian operator, but a numerical parameter labeling reference frames. Then we have to admit that time and space coordinates have radically different physical meanings. And joining them into one four-dimensional spacetime, either flat or curved, does not make sense. This may look like a bad news. Einstein-Minkowski relativity is not compatible with quantum mechanics, and quantizing general relativity is not going to produce a consistent quantum theory of gravity. But not all is lost. There is an encouraging news. I am talking about the Wigner-Dirac relativistic quantum mechanics, which is a promising candidate for quantum gravity. What do I mean by Wigner-Dirac relativistic quantum theory? Their idea was very simple. The basic postulate of relativity says that all inertial frames of reference are equivalent. Wigner and Dirac simply applied this principle to quantum mechanics. Wigner's work set up the basic requirements for a relativistic quantum theory, and he described in detail how to apply this principle to simplest quantum systems, elementary particles. Dirac extended these ideas to multi-particle systems and explained what does it mean for an interaction to be relativistic. These works showed clearly that the Hilbert space of any relativistic quantum theory must carry an unitary representation of the Poincaré group. The Poincaré group is the most fundamental object in relativity because this is the group whose elements are transformations between different inertial observers. Please note how this definition of relativistic invariance is different from four-dimensional space-time ideas of Einstein and Minkowski. The space-time is not even mentioned in the Wigner-Dirac theory. From the theory of Lie group representations, we can conclude that unitary representation of the Poincaré group is accompanied by a representation of the group's Lie algebra with Hermitian operators. Here I listed the commutators of these generators that follow from the Poincaré group structure. This set of relationships has everything we need to know about the theory of relativity. The representatives of Poincaré algebra generators are operators of observables with very clear physical interpretations. The generator of space translations is the total momentum of the system P. The generator of rotations J is the total angular momentum. The generator of time translations H is the Hamiltonian or the total energy, and the generator of boosts K is less familiar. It is the product of the center of mass position and total energy. Let us now see how this theory works in multi-particle systems. If the particles are non-interacting, then the total observables are sums of one-particle observables. It is common to mark the generators of the non-interacting representation by the subscript 0. Interaction is introduced by adding extra terms to these operators. Note that in the relativistic case, we cannot simply add potential energy V to the Hamiltonian. To preserve the Poincaré commutation relations, we have to add an interaction term Z to the boost generator as well. Now, I have outlined two approaches to relativity. One is the Einstein-Minkowski spacetime approach, which most of you are familiar with. The other is the Wigner-Dirac idea about unitary representations of the Poincaré group. What is the connection between these two theories? Are they two sides of the same coin? Or perhaps there is some disagreement? To answer these questions, we can try to derive Lorentz transformations of special relativity within the Wigner-Dirac theory. Here is the idea how to do that. We know that in the classical or non-quantum approximation, particles move along well-defined trajectories. So when trajectories of two particles intersect, they create an event well localized in both space and time. In each reference frame, this event will have certain space and time coordinates. If we use the Wigner-Dirac method, we will know how transformations between inertial observers are represented in the Hilbert space, so we should be able to transform particle trajectories from one observer to another. This means that we will be able to transform the coordinates of the events' intersections from one observer to another and compare these transformations with Lorentz formulas. This is the plan. Of course, we are most interested in boost transformations. Let us start from the simplest case of non-interacting particles. In the left panel, I've shown space-time worldlines of two particles, blue and brown, which intersect at a point with the time coordinate ct and space coordinate vector r. From the point of view of a moving observer, the worldlines will be different, of course. They are shown in the right panel. The intersection point ct prime r prime can be easily calculated in the Wigner-Dirac theory, and remarkably, the primed coordinates are related to the original coordinates exactly by Lorentz formulas of special relativity. So we conclude that special relativity works well for non-interacting events, at least in the classical limit where particle trajectories make sense. Let us now repeat the same derivation for interacting particles. The interaction has to be relativistically invariant in the Dirac sense. Apart from that, it doesn't matter which type of interaction we choose. For example, we can imagine two charges moving freely and interacting by a Coulomb-type force. Then it can be shown that the coordinate transformation is no longer given by the universal Lorentz formulas. The exact transformation now depends on the strength of interaction, on the state of the particles, and other details. One can trace the source of this discrepancy to the presence of the potential boost interaction term Z. This result has been known in the literature since 1963 under the name of Curie-Jordan-Sudarshan no interaction theorem. Let us now assume that gravity is the same kind of force, similar to the electromagnetic Coulomb interaction, and that it can be described by the Wigner-Dirac theory. Of course, first we have to deal with relativistic invariance. In the original Newtonian theory, the boost interaction Z was absent, so the relativistic criterion was not satisfied. We don't have the exact solution of this problem, but there are methods allowing one to enforce Poincare commutators approximately by representing interaction operators in the Hamiltonian and boost as series in inverse powers of the speed of light. For example, if for the potential boost we choose the blue operator, we will get much closer to satisfying the Poincare commutators. Even better agreement with relativistic invariance can be achieved by more terms of higher orders of the inverse speed of light. Unfortunately, obtaining exact relativistic invariance of the gravitational interaction is an unsolved problem, but it is a technical problem which is fully understood, and we will not spend our time on it. The relativistic invariance alone does not fix these additional terms in the Hamiltonian in a unique way. Some degree of freedom remains, and we would like to use this freedom to choose our interaction for a better agreement with observations. One condition is that this interaction should be able to describe the Mercury's perihelion shift. The left panel shows that in the traditional Newtonian theory, the orbit of a single planet, such as Mercury, would be a perfect ellipse. However, as shown in the right panel, the true orbital ellipse is doing a complicated dance by shifting its axis counterclockwise by 43 arcseconds per century. This shift can be explained by the so-called Einstein-Infeld-Hoffmann Hamiltonian. The additional relativistic corrections are shown in blue. Originally, these corrections were derived in a certain approximation from Einstein equations of general relativity, but we will incorporate this Hamiltonian in our theory without mentioning its origins. Another remarkable feature of gravity is that it obeys the so-called principle of equivalence. Sometimes this fact is formulated as an equality of the inertial and gravitational masses. It is important to realize that the total mass of any body is not equal to the sum of masses of its constituent particles. In addition to the sum of particle masses, the total mass includes also a negative defect of mass caused by particle interactions with each other. The defect of mass is negative because any compound body is usually held together by attractive forces that lower the total energy. For example, electromagnetic or chemical attraction in atoms and molecules contributes a tiny fraction to the total mass of a body. The nuclear attraction lowers the mass of protons and neutrons in nuclei by about 1%, which is a sizable fraction. This brings us to the remarkable conclusion that gravitational forces act not only on particles and their masses, but also on interacting energies between the particles. One side effect of this property is that all objects fall with the same acceleration. And this property was confirmed by multiple experiments, starting from Galileo, who dropped a bullet and a cannonball from the Leaning Tower of Pisa and saw how they reached the ground at the same time. An experimental breakthrough was made by Hungarian physicist Laurent Eötvös, who perfected the accuracy to 1 part in 100 million. This was sufficient to confirm the effect of gravity not only on nuclear interaction energies, but also on electromagnetic interactions in solids. All these properties have very elegant explanation in general relativity, because in this theory gravity is not a force, but a change of geometry. So it's not a surprise that in general relativity, gravity has the same effect on all forms of energy. Returning to the quantum Wigner-Dirac approach, if we admit that the source of gravitational field is not mass but energy, then it would make sense to rewrite the Einstein-Infeld-Hoffmann-Hamiltonian using Hamiltonians of the two interacting subsystems rather than their mass operators. Note that if in this expression I approximate subsystem Hamiltonians with the sum of rest energy mc square and non-relativistic kinetic energy p squared divided by 2m, I'll obtain the original Einstein-Infeld-Hoffmann Hamiltonian. But here we meet a significant problem. The Hamiltonian written above cannot be regarded as the ultimate Hamiltonian of the quantum theory of gravity. Indeed, this Hamiltonian presumes that we manage to separate the full physical system into two localized objects, for example, Sun and Mercury. This assumption is not applicable in many cases. So the question is, can we write the gravitational Hamiltonian in a more general and universal form? Here is an idea of how this can be achieved. It appears that under very general assumptions, the non-gravitational Hamiltonian of any isolated system, such as a hydrogen atom or solar system, can be written as a space integral of a properly defined operator of Hamiltonian density. All forms of energy can be represented in this way: kinetic energy, the energy of electromagnetic interaction, nuclear interaction, and so on. But if it is so, then the full Hamiltonian that takes into account also gravitational energy can be written as follows. The first term is the non-gravitational part, and the second term is the gravitational interaction of the energy density with itself. Probably some higher order terms can be added. They are shown by the ellipses. But already in this simple notation we get a Hamiltonian that satisfies the requirements of the equivalence principle. Indeed, it can be shown that when our system separates into two spatially isolated subsystems, 1 and 2, then the above Hamiltonian takes the form we considered earlier. The gravitational light bending is another effect which is often regarded as a definite proof of general relativity. This effect was predicted by Albert Einstein and then confirmed by Arthur Eddington, who measured positions of stars during the sun eclipse in 1919. Actually, light bending is expected also in the Newtonian theory. One can simply assume that photons fall with the same common acceleration g. But then the bending angle is twice smaller than Einstein's prediction and Eddington's measurement. Einstein's theory explained that the other half of the bending angle is a purely general relativistic effect related to the distortion of the global spacetime geometry. Can Wigner-Dirac theory of gravity explain this double bending angle effect? Yes, it can. To demonstrate that, let us adjust our Hamiltonian to the particular system sun plus photon. Sun variables have index 1, and we will assume that sun's momentum is 0. Then sun's energy is simply a constant mc squared. Photon variables have index 2. Photon's mass is 0, and photon's energy is momentum times speed of light. By making these substitutions, we obtain the following approximation for the non-interacting Hamiltonian H0, and from all the interaction terms, only two survive, which are shown in blue. The second blue term is normally a small relativistic correction, but in the case of a massless photon, the magnitude of this term becomes exactly the same as the primary Newtonian interaction. This is why in the resulting full Hamiltonian, the sun-photon interaction energy is twice larger than in the naive theory based on the equivalence principle. Now, once the Hamiltonian is defined, the photon bending angle calculation is a simple technical matter. In the zeros approximation, we can assume that the photon moves along the unperturbed straight line showed here by the dashed arrow. At each point of this trajectory, we can find the gravitational force acting on the photon by solving the first Hamilton's equation of motion. The force is minus the derivative of the Hamiltonian with respect to the photon's position. Next, by integrating the z component of the force along the full trajectory, we will obtain the total accumulated z component of the photon's momentum. Then the tangent of the bending angle is given simply by the ratio of the gravity-induced z component to the total momentum. This calculation yields the bending angle of 1.74 arcseconds, which coincides with the prediction of special relativity and astronomical observations. We can also apply the second Hamiltonian equation of motion, which expresses velocity as momentum derivative of the Hamiltonian. The factor in parentheses is slightly lower than unity. Therefore, this result can be interpreted as a slowdown of light near gravitating bodies. The speed of light becomes lower than c. This effect was named Shapiro time delay and confirmed by observations in 1966. Therefore, we conclude that both general relativity and Wigner-Dirac theory can be used to describe the light propagation near the Sun or other massive bodies. Let us now return to the Einstein-Infeld-Hoffmann Hamiltonian of two massive bodies. For simplicity, I'll drop relativistic corrections. I'll also assume that one of the bodies is Earth at rest, and the other body is an arbitrary physical system on the Earth's surface. So the total quantum Hamiltonian in this approximation has three terms. First is the Earth's rest energy. Second is H with hat, the non-gravitational Hamiltonian of our physical system. And the third one is the gravitational interaction. Let us now drop the Earth's rest energy, which is an irrelevant constant, and rewrite the full Hamiltonian in the form of H hat multiplied by a quantity in parentheses. This means that the Hamiltonian of any physical system placed in a uniform gravitational potential is multiplied by a numerical factor. This factor beta is always less than unity because gravitational force is always attractive. This effect was confirmed experimentally in 1960 by Robert Pound and Glenn Repka. If the physical system we are talking about is a nucleus of iron atom, then near Earth's surface the separations between its energy levels are expected to shrink by the factor beta. Energies of gamma rays emitted in transitions between these energy levels also decrease. But for another iron nucleus at a higher elevation, the factor beta will be closer to unity. Energy gaps will be larger and out of resonance with gamma rays emitted from downstairs. Then the upstairs iron nucleus will lose the capability to absorb these gamma rays. The theoretical value of the beta factor was confirmed in an ingenious Pound-Repka experiment. The scaling of Hamiltonians by beta factors has another remarkable experimental manifestation. As we well know, in quantum mechanics, the time evolution of any isolated system is described by the time evolution operator, which is an exponential function of the system's Hamiltonian. On the Earth's surface, the Hamiltonian is multiplied by the factor beta. This means that all processes in the system go 1 over beta times slower. This slowdown was confirmed in experiments. Moreover, this effect has to be taken into account by the software in GPS satellites, because otherwise a huge loss of position accuracy would result. Let me now summarize my conclusions. All previous attempts to quantize general relativity were not successful because the fundamental postulate of this theory, the equality of time and position coordinates, contradicts the basic postulate of quantum mechanics, the inequality of time and position. The alternative approach to quantum gravity can be based on Wigner-Dirac relativistic quantum mechanics. This theory has a number of advantages. First, it's fully quantum by design. The relativistic invariance can be enforced rather easily, and there are no difficulties in explaining various observations that were interpreted previously as evidence in favor of general relativity. Here is an incomplete list of such observations: Mercury's orbit precession, light deflection or bending, Shapiro time delay, universality of gravitational acceleration, gravitational redshift and gravitational time dilation. Thank you.